The first example of proof by induction I will do is to show that the sum of the first n natural numbers is given by n times n plus 1 over 2. Now, let's just see that this formula works, say, for n equals 4. I'll just do one or two test cases. So if n equals 4, we have 1 plus 2 plus 3 plus 4 is the sum of the first 4 natural numbers. 1 and 2 is 3, 3 and 3 is 6, 6 and 4 is 10. This works out to 10. Now if we plug 4 into this formula on the right hand side, we should also get 10. Plugging 4 in here, we have 4 times 4 plus 1 divided by 2. That's 4 times 5, which is 20. 20 divided by 2 is 10. So you see that this thing is indeed true, at least for n equals 4. Now, of course, we want to prove that this thing is true for all values of n. So, the first step in the method of proof by induction is to prove that this statement here is true for the smallest value of n. So the smallest value of n that is involved in this problem is n equals 1. So we want to prove that this statement here is true for n equals 1. Now sometimes this is abbreviated to p of 1. All of what I've written down here. It means we're trying to prove this statement is true for n equals 1. So if we let n equal 1 on the left hand side, well, we just have the sum of the first 1 natural numbers. Well, that's just 1. That's just the first natural number actually. And on the right hand side we have 1 times 1 plus 1 over 2. We just plug 1 in for n into this formula here. So we get 1 times 2 on top, which is 2. 2 divided by 2 is 1. So the right hand side is 1 and the left hand side is also 1. The left hand side is just the sum of the first 1 natural numbers. Well, that's just the first natural number. So we get the same thing on both sides. So this is indeed, our statement is indeed true for n equals 1. The second step in the method of proof by induction is to assume, and I've assumed written in capital letters, that the statement is true for n equals k. So k is some number, some natural number greater than or equal to 1. So it could actually equal 1. So k could be 1 or 2 or 3 or 4 or any natural number. So the p of k that I've written down here stands for the proposition. You know, we're looking to see if the proposition is true for n equals k. Actually, we're just assuming that the proposition is true for n equals k. So that means if we take the sum of the first k natural numbers, then we will get k times k plus 1 over 2. So we are assuming that this thing is true. Step 3, under the assumption that proposition k is true, prove that the statement is true for n equals k plus 1. So what we need to do now is to assume that this is true. So we need to build on this. And by building on this, we want to prove that our statement, which is this up here, is true for n equals k plus 1. So how do we prove that the statement is true for n equals k plus 1? Well, we would be summing the first k plus 1 integers, and we would be plugging k plus 1 in for n, in n times n plus 1 over 2. So we need to start with this and build on it. So what we do is we add k plus 1 onto this. Okay, I'll just highlight that part. And if we add k plus 1 onto the left hand side, we must add it onto the right hand side. Okay, we must do the same thing to both sides of this. So we are assuming that this is true. And if this is true, we haven't changed anything by adding the same thing onto both sides. So just to remind you, here is what we want to prove. Well, not just to remind you, but to just make explicit what we want to prove. We want to prove that the statement is true for n equals k plus 1. So if we sum the first k plus 1 natural numbers, this is what we will get. 1 plus 2 plus 3 plus dot 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 as far as the kth natural number, which is k, and then we as far as the k plus first one. So this will be the last natural number. of the first k plus 1 natural numbers. It's just k plus 1. We would have to plug k plus 1 in for n, so we would have k plus 1 here times k plus 1 plus 1, which is k plus 2, and that's divided by 2. So this is what we want to prove. So we need to build on our assumption to prove that. So we've started doing that by adding k plus 1 onto both sides of this here. So you see now at least that the left hand side is equal to the left hand side of what we're trying to prove. So it remains for us to show that the right hand side will equal k plus 1 times k plus 2 over 2. And then we're done. So I've written this over here, and we just have to write this in hopefully this form here. So we can get a common denominator of 2, and we've 2 into 2 goes once, 1 times k plus 1, k times k plus 1 is k times k plus 1, plus, now we divide 1 into 2, which goes twice, 2 times k plus 1 is 2k plus 2. And we can multiply this out. We get k squared plus k plus 2k. That's k squared plus 3k plus 2 over 2. And k squared plus 3k over 2 can be factorized into k plus 1 times k plus 2 all over 2, which is equal to this here. So we've proven that if the statement is true for n equals k, in other words, the sum of the first k natural numbers equals k times k plus 1 over 2, then the statement is true for n equals k plus 1. In other words, the sum of the first k plus 1 numbers is got by replacing n with k plus 1. If we replace n with k plus 1, we get k plus 1 times k plus 2 over 2. So here I've tried to shorten everything that I said. So we've shown that if the statement is true for n equals k, then it is true for n equals k plus 1. In particular, if the statement is true for n equals 1, and we actually know that it's true for n equals 1, that was step 1 of proof by induction, which I've actually erased, but that was in step 1 we proved that this statement is true for n equals 1. We just summed the first one into natural number, which is just 1, and then we plugged 1 in for n, and we got 1 equals 1. Then the statement is true for n equals 1 plus 1, which is 2. So if it's true for n equals 1, it's true for n equals 2. We know it's true for n equals 1, so it must be true for n equals 2. And we can continue on with this. If the statement is true for n equals 2, then we know it's true for n equals 2 plus 1. We just put 2 in for k, so we know it's true for n equals 3. So here I've written in one more value of k. If it's true for n equals 3, then it must be true for n equals 3 plus 1 equals 4, and so on. So it'll be true for n equals 5, n equals 6. So the statement is true for all natural numbers. So that's the logic of proof by induction. So here is our statement, and we've proven that it's true for all values of n, all natural numbers n. Sometimes for all is this symbol here. It's like an upside down capital A.